So next we have Shauvik Choudhary, who is going to talk to us about, and I cannot remember the title of it. There we go. Using robots to test your Android app. So take it away.
Hi, everybody. This is my second time at GTAC. Last time I led a a roundtable discussion on cross-platform mobile testing, and now this time I'm glad to come back to talk about using robots for app testing. So so one thing, right? So I'm going to talk about software robots, and not like the OptoFidelity guys who showed a real robot, right? So a disclaimer at the start, and let me tell you a little bit about myself. So I got my PhD from Georgia Tech in summer. My thesis was in the lines of how to do better cross-platform testing and maintenance for web and mobile applications, right? And over the past few years, I've been lucky enough to work at several companies, got a lot of industry experience, and in the past 1 year, I have been taking part in the different entrepreneurship programs at Georgia Tech, and that has led me to Checkdroid, which is an early stage startup. So if you have any inefficiencies that you guys think in testing, reach out to me, find me during the break. So today's talk will be mainly focused on presenting results from this research paper that we wrote, right? So automated test input generation techniques for Android. Are we there yet? That's a question that we are trying to address in this paper. And my collaborators for this project were my advisor, Dr. Alex Orso, and Alessandra Corla from MDS Software Spain. This paper will be presented in 2 days in Lincoln, Nebraska at the ASE conference. OK, so we want to use robots for testing, right? Now, but let's first see how a test structure looks like. So we all are familiar with this, right? Test structure has 4 different steps. At start, you'll have the setup phase where you'll initialize your environment and get it ready for testing. The next phase is the exercise phase. And what you do here is that you interact with the app, provide it inputs, and exercise it, right? In the next step, which is verify, you will check whether the app came in expected state or not as a result of the inputs that you gave it. And final step is the tear down step, where you clean up the environment and get ready for the next test, right? So how will a robot or an automated technique do these steps, right? So let's say we have a robot. For the setup phase, it can say that, OK, let me start the app, right? Let me install the app on the device, and let's start it, right? For tear down, it can say, let me stop the app and uninstall it, right? For verify, it says that, OK, let's have an oracle or a policy that the app may not crash. It might not show any issues that you can identify. But the most important or the most challenging thing for such a robot is what input should it give the application so that it could meaningfully exercise the application, right? And this is the main focus of this talk, where we are going to evaluate existing input generation techniques, right? So let me first introduce you to the simplest, and maybe most of you should already be familiar with the Android Monkey tool. So who here has used the Android Monkey tool? Many of you, right? So this is a tool which comes as a part of the Android SDK. If you have the Android SDK installed, you should have this tool. And you can invoke it using ADB shell, right? So you can say ADB shell, give it the package name for your app, and give it a number of events, let's say 500, right? And what it will do is it will just pick random events and throw it at your app to invoke it and to make it do different things, right? And this tool also has some advanced options, right? So since it's using randomization, you could set a number seed for the randomization, right? You could also throttle this tool, right? You could tell it that, OK, between different events, give this much timeout, or give this much wait for these many milliseconds. You could tell it that when choosing the different events, right, focus more on this kind or this category of events. So you can give a percentage distribution. And by default, this tool will stop after it finds the first issue, right? So you can tell it to ignore issues like exceptions or timeouts and so on, right? So this is one example of a robot, right? And we looked at academic papers and industrial tools and found that there were several such tools which were out there in research papers and in blog posts, right? So we wanted to see how do these tools compare against each other, right? And is there need for additional research yet, right? So that's the question we asked. For these test input generation tools, have any of these tools solved the problem, and are we there yet? So that was the question we were asking. And while doing this study, we considered these tools as robots, right? So we considered them as push-button techniques. You give this tool your app and start it, and it should test your app and give you all the problems that your app has. Right? So let me clarify a little bit the goal of testing in general, right? So goal of such a robot would be to make the app crash, and also to exercise the different behaviors that are there in the app, right? So if the robot exercised a particular behavior or a particular functionality of your app, and if it could not crash that functionality, then you have at least some level of confidence, right? So and for this, typically coverage is the weight or a proxy to measure this kind of a thing. Okay, so now each of these tools is different from the other based on the strategy it uses, and I'm going to show you 4 things that actually form the tool strategy. The first is the instrumentation strategy, right? So each tool has to interact with the app and know or understand what happened as a result of this interaction, right? So the tool might modify the app by injecting probes in it, or it might modify the platform to know what's going on in the platform, right? So this is what I mean by instrumentation strategy. The next one is that, does the tool interact with the application only through the UI, or does it also send system events? So for example, parts of your app might be triggered via external notifications or via SMSs, right? Let's say your system gets an SMS and your app is listening to that, right? So if in order to trigger such functionality, you will have to send these system events, right? So you wanted to see which tools do what. The third one is, does the tool require the source code of the app to do the testing, or can it do it in a black box fashion, right? And the fourth, or the most important strategy, is the exploration strategy, right? And this decides how this tool is going to explore the state space of the application, right? And I'm going to cover this in more detail, but there are 3 such strategies, right? Random, model-based, and systematic. So let's dive into this a little bit and look at the different exploration strategies that these tools have. So the first one is random, right? So here it's just like rolling a dice and picking a random number, right? So these tools, the tools in this category, Monkey and DynoDroid, what they do is they randomly select events and they just throw it at the app, right? So the good part about this is that you can do this efficiently, right? You can randomly pick so many events and throw it at the app, right? However, and also it makes it very suitable for stress testing, because you can see how well your app behaves when so many events are thrown at it, right? However, the problem with such techniques is that they are hardly specific. You can hardly tell Monkey that, okay, Monkey, make my app go to this particular activity or this particular state, right? So they are not specific. They are not agnostic. They are agnostic of the behavior, right? So if you have already covered some functionality, you will the tools don't consider that, and they might have redundancy in the events that they supply. They might be testing the same thing again and again, right? And finally, these tools have no stopping criterion. They don't know have they tested enough, right? So typically, as I showed in Monkey's case, you give it a number of events to fire, right? Other approaches could be to have a timeout, like let's say test my app for 1 hour, right? And then tell me what all you found, right? So this is about the random exploration strategy. Now let me talk about the second strategy, which is the model-based exploration strategy, right? So these tools, what they will do is, as they are exploring your application, they'll build a model of the application, right? And this model is typically GUI-based, or GUI-based model, which can be, an example of this model is shown on the right-hand side for the dialer application, right? So this is the graph-based model where the states are different GUI screens, right? And the edges are transitions or actions that you do in these states to go into another state or screen, right? So the tools in this category are A3E, Swift10, GUI Reaper, Puma, and Orbit. And intuitively, these tools are more effective because you know what they are testing. And these tools are also less redundant because once they know that, OK, I've reached this activity, right, and I've seen it before, I don't need to test it again, right? So they are less redundant than random tools. However, these tools only consider the GUI state space, right? They don't know what is going on behind the GUI, right? So they cannot model them. They currently don't model them in the model. Okay. Now let's look at the third category, which is systematic exploration strategy, right? So these tools, what they do is they use sophisticated techniques like symbolic execution or evolutionary algorithms to systematically cover the state space of the application. So the two tools in this category, Active and EvoDroid. So for the first tool, Active, it uses symbolic execution. What it means is that it collects constraints from within the application when it's executing. So for example, on the right-hand side, you can see a constraint which is on the X and Y coordinate that the tool has to click, right? So once it gets this constraint, it can pass it to a SAT solver, get some solution for this constraint, and use that to test, right? Once you have tested this path, you can flip this condition to get other paths, and you can test other paths, right? So this is one way these tools operate, right? And the good thing about these tools is that they can systematically explore, right, more than, and they can, you can direct the testing towards one particular path, right? However, because in these techniques are heavyweight, they are less scalable than random, right? So these were the three different exploration strategies, and we considered a subset of the tools because the other tools they were not available, right? They were only in a research paper, but they were not open source or available for testing, and some of the tools were focused only on testing a very specific part, right? And they were not general enough. So as I show in this table, these are 7 tools. Monkey is from Google, right? The other tools are academic tools: Active, DynaDroid, A3E, SwiftHand, GUI and Puma, right? The second column shows if the app or tool needs instrumentation or not. Does it modify the app or the platform, right? And as we can see, Monkey does not, and Puma, which is the last tool, it does not modify anything, right? So Puma uses the accessibility API, and through that it can know the status of your app. Whereas Active, that tool modifies both the platform and the app, right, to get the symbolic constraints. DynaDroid modifies the platform, whereas the other 3 tools modify the app. As far as the next column shows, what are the events that the app supports or the tool supports, right? So all the tools support UI events. They can interact with the application through the GUI, right? Whereas only 2 tools, Active and DynaDroid, support system events. I explained the exploration strategy before, right? So as you can see in this, 2 tools, Monkey and DynaDroid, are random tools. A3E is systematic, and the other 4 are model-based tools, right? And out of all these tools, only Active needs the source code of the app. All the other tools can operate in a black box fashion. So now that I have introduced you to these tools, let me tell you about our experiments and how we evaluated these tools. Right? So for doing our experiments, we had 4 research criteria. The first one was how easy is the tool to set up and use, right? And the second criteria was what are the different versions of the Android framework that these tools support. The third one was how much coverage can these tools achieve on general subjects. And the fourth was what is the fault detection capability, or can these tools reveal failures in applications, right, automatically. So for our experiments, we used 68 open source subjects. All of these were used in some or the other tool's own evaluation, but we considered a union and even more subjects, right? And as you can see, this shows the distribution of the subjects and the categories from Play Store. So for our experiments, we ran them on a Linux Debian machine, right? Since we wanted to have repeatable experiments, we used virtualization technology. We used VirtualBox for that, and Vagrant to control the VirtualBox. On top of this, we had an Ubuntu guest on which we had the emulators running, right? So for our experiments, we chose 3 versions of the Android emulator, 2.3, 4.1, and 4.4. And this was because some tools were specific. You wanted specific versions of the Android emulator, and KitKat was the latest when we did this experiment. So what we did was on the Ubuntu guest VM, we installed this tool. We removed any default timeouts that these tools have, so that we wanted to run all the tools for a specific time, right? and we used their default configuration, which means that we did not tune any specific tool to avoid bias. So now let me now that I've shown you our experimental setup, let me show you how we did this experiment, right? So what we did was we took each tool, and for each benchmark we ran it for 1 hour, right? Then we since there can be non-determinisms in while running the Android SDK, right? Things can crash, things cannot behave in a deterministic fashion. So to account for these things, we ran these experiments 10 times and ignored anything that was outside the standard deviation, right? Results. And then we collected reports, right? So for the results, we collected 2 things. The first thing was every 5 minutes we collected the coverage report. How much did the coverage improve over time? That's what we collected. And we also collected the logcat, or the logs from the device from which we extracted failures. Okay. So specifically what we did was we used the default EMMA tool. And EMMA, if you know, it does not give you statement by statement level coverage information by default. So it's present in the HTML reports. So we extracted this information from the HTML reports. And for logcat, what we did was we wrote a custom parser based on regular expression, which extracted unique stack traces, right? So we wanted to have unique stack traces to find different failures. And we verified these manually to make sure that our parsing logic was correct. Okay. So now let me show you the results, right? So for the first 2 research criteria, ease of use and Android compatibility, we manually set up these tools in our infrastructure and evaluated them. So as you can see, 2 tools, Monkey and DynoDroid, required no effort. That was because Monkey comes as a part of Android SDK. We did not have to do anything, right? In the case of DynoDroid, the authors actually released a virtual machine. So it was very easy for us to reproduce and recreate their experiments, and we could easily use the tool. For 2 tools, A3E and Puma, we had to spend a couple of days to fix minor bugs, and we got them running. For 3 other tools, Active, Swiften, and GUI Reaper, it took us weeks to interact with the developer because these tools were not maintained anymore, but we finally got them running. Right. As we can see on the 3rd column, Active and DynoDroid, they both of them modify the framework, right? So however, they have a tight dependency on the framework version, and the version they provide only works for Android 2.3 Gingerbread. Swift Hand supports Android 4.1 Plus because that's what it was built, and Puma supports Android 4.3 Plus because it uses the accessibility API, which was majorly enhanced in 4.3, right? And 3 tools, Monkey, A3E, and GUI Reaper, can work on any version of Android. Okay, so now let's get to the coverage results. So this graph shows you the coverage, the distribution of coverage, for across all the different apps for all the different tools, right? So as you can see in this graph, for some applications, most of these tools were able to get high coverage, but the median is very different, right? So for example, both Monkey and DynoDroid have high median values, whereas the last 3 tools have very low median values. So let me show you the next result, which shows you the progress of coverage over time. So this graph shows you, how the coverage improved over time. So as you can see, in the first 5 minutes, all the tools were about to, we could quickly get, about almost, their max coverage, which is 40% coverage, right? So this shows that even if we had run this experiment for another hour, it would have still been flat, right? So it wouldn't have improved the results drastically. The only exception here is the pink line, which is the GUI Reaper tool. What that tool particularly does is it creates VM snapshots at intermediate steps, and it restarts the application from those snapshots. And that's why, because of this continuous restarts, it takes a long time for that tool to reach its max coverage. Okay. Now let me show you the next result. So this shows the mean of coverage across all the different tools. So as you can see, for some apps, all tools could get 80% or 90% coverage, whereas for some apps, they got really less coverage, but most of the apps were in the middle, right? So we wanted to understand why, and we saw that on the right hand of the spectrum lied very simple apps. Some of these were samples from Google, right, and they had a very limited state space. So all the tools could get decently high coverage on them. On the left side of the spectrum were tools or were apps which required, for which none of these tools was able to cover enough safe space. We looked at these apps and found that these apps required a lot of manual configuration. So for example, the first icon there represents K9 Mail. It's an email client. It requires you to set up an email server, set up that configuration, right? And for our experiments, it was not possible because it's an external dependency that we have to reset after every experiment. So, but we found that this was a great learning that for such tools, it is harder to test them by any of these automated robotic testing tools. Okay. So now let me show you results from the fault detection ability. So here, what we did was we counted the different failures that were invoked by these tools, right? And as you can see, the failures are colored, which means which shows the different packages they belong to. For example, the blue color represents the java.lang, and one representative exception in that package is the null pointer exception, right? So as you can see, in the case of Monkey, it could get a lot more java.lang exceptions, right, than other tools, right? Whereas for a tool like Puma, it got java.io and java.lang, right? And the pink colored exceptions are the custom exceptions, which were defined in the app itself, and only two tools, which is Monkey and SwiftRun, could reveal those exceptions. So we also wanted to compare these tools pairwise, which means that each pair of these tools. And the next graphic is going to show you that. So in this chart, above the diagonal, you see the coverage results for every pair of tools. Below the diagonal, you see the failure results for every pair of tools. And let me explain this a little bit more detail. So let's look at coverage. So here you can see that two tools, Monkey and DynoDroid, they had 43% of statements were covered by both of these tools, right? Whereas 5% of statements in the subject applications were only covered by Monkey, and 8% were only covered by DynoDroid, 9%. Similarly, for the failures, as you can see, 6 exceptions or 6 failures were common between GUI Reaper and A3E tools, whereas 40 were invoked by GUI Reaper and 24 were invoked by A3E. So now that I've explained you this, we can see in the overall graph that in the statement coverage, we still have there's a lot common between the tools, right? But there is a lot more that needs to be covered, right? Most of these tools just reach 50%. And for the exceptions, as we can see, there's very less common between the tools. So you need more than one tools to expose those different failures, right? So our first observation is that random approaches seem to be doing their job, right? Random approaches seem to be effective in this context, right? DynoDroid and Monkey both did well, right? So let me now present you our findings, which I'll split in 2 different categories. The first is best practices that we saw in some tools which made them stand out, right? And limitations that we saw in tools that none of the tools implemented these practices, right? So let's talk about best practices. So the first thing was that tools like DynoDroid, what they did was they sent system events, right, which can for example, SMS, right? So if your app is listening for SMSs, you wouldn't reveal any failures in that part of code unless you send a system event to it, right? So this was a very good feature of those tools. Then, as I mentioned to you, the tool GUI Reaper took a long time to get its max coverage. So for efficiencies, tools should minimize the restarts in the applications that they have. This is a very common problem for robotic crawlers, right? So what these tools do is they get stuck whenever they see a screen like this, but because a robot will not know what to enter here, right? So specific tools like GUI Reaper and DynoDroid, what they did was they allowed to in the configuration you could specify the different username password pairs, right, or different values that the robot could then use and get past such screens. then an application's the behavior is dependent on the start state. For example, for the mail client, if there is no email messages in its content provider, it will not expose any behavior, right? So tools like GUI Ripper allowed the specification of different starting states by loading the app in that particular starting state, right, and letting the tool run after that. And the final one is that in our experiment infrastructure, we use virtual machines, right? So we could clear everything after the experiment. But some of these tools, what they allowed for is a partial cleanup, right, of uninstalling the app and clearing its data, right? So we thought that that was also a very good feature in these tools. So now let me talk about some limitations or future work that these tools need to improve on. So the first one is reproducibility, right? So a robot might make your application crash, but it's very hard to actually look at the robot's log and to figure out what did it do to crash the application, right? We believe that such things should be a part of the tool's output, right? It should give you a test case, ideally, that you can run to reproduce that kind of bug. And we thought that none of the tools had this. The next thing was that since when you're testing, you always test in a hermetic environment, right? And none of these tools allowed for you to specify mocks, and they all interacted with the real systems. The third one was that while you're doing testing, there can be some harmful operations. Let's say you're testing the Uber app. You might, if you're not testing it in a right fashion, you might actually order a real cab, right? Or you might send out emails or SMSs, right? You don't want to do that. So none of these tools allowed for sandboxing, right, to avoid these side effects. And finally, we all are familiar with this picture, right? So there was no robot or no tool which was focused on finding issues that are across different devices, right? So none of them were targeted towards cross-device testing. So in summary, what I showed you was, I motivated the fact of how you can use a robot to do the testing. I showed you different exploration strategies that current tools use, right? I showed you details about our experiments and the results. And I've showed you some best practices and limitations in existing tools. So all our the virtualized infrastructure is available at this URL. You can also go to my website, Shauvik.com, and get a link to that. So that virtual machine has all these tools installed already with all the subjects that we used. So you don't have to go and build these tools from source. You can just get this and use it in your projects. And that brings me to the end of my talk. Thanks.
Thank you. I think we have time for a few questions. So first off, do you have any recommendations for iOS robots?
Yeah, so there is a tool called UI AutoMonkey. It's available on GitHub. It's the counterpart of Monkey for iOS. It uses the UI Automator API, right, that iOS has. So you could use that.
These tools may be able to find app crashes, but how do you then come up with a repeatable set of steps that can reproduce the problem and help find a root cause?
Yeah, so this is actually the hard part. So for example, in Monkey, you can ask it to be verbose, right? And Monkey will tell you that, OK, it did these steps, right? And then you see this exception, right? So what it means is that you have to go through all these steps, and you have to find a minimal set of steps, right? You have to reduce this to a minimal set of steps that can help you, find that problem, right? So this is actually a very hard thing, and we are working on, some of these areas, right, to generate test cases. But yeah, so there's currently no easy solution for this.
Can you propose a new way to compare the quality of tests generated by these tools beyond those of coverage and crashes?
So, so coverage and crashes, of course, I showed it. Another thing is that, OK, your test cases, right? If you have, you should have a minimal set of test cases that can generate, the same errors, right? So let's say if you have 100 test cases that give you 5 errors versus you have 5 test cases that can give you 5 errors, right? So these tests, and of course, the same coverage as well, right? So having a minimal set of test cases is also something that people, look out for, because then you can run these test cases fast, right, instead of running redundant tests.
Cool. And I think that's all we have time for. So thank you very much.
Thanks.